We'll be looking at a variety of topics this unit, starting out just by looking at things moving in circles. Then we'll look at universal gravitation, which is gravitation that applies to any two objects with mass. And the reason why these two things kind of tie together is Kepler's laws of planetary motion, because it's gravity that causes those planets to move in nearly circular orbits. But to start out with, we're just going to look at the forces and the acceleration that apply to objects moving in circles. So I want you to start out by thinking about three different situations. The first is if you've got a frisbee, and this is like top-down view. You got your frisbee upside down, and if you have a golf ball rolling around the frisbee, say in that direction, as you're holding the frisbee maybe and swirling this ball around. So the ball is going roughly in a circle. And if we think about that, what forces are acting on the ball? Well, there's a normal force coming out of the page from this perspective and gravity going down into it, but that's not too informative. Those are balanced forces. But what is causing it to go in a circle rather than a straight line? Well, there's the outer wall here, and it's in contact with the ball, so the only direction that outer wall could push is toward the center of the circle. So there would be a force here. When the ball is in this location, the force would again be toward the center. When the ball is here, it would be there. When it's here, it would be here. So there's your forces for a ball rolling around the inside of a frisbee. Another situation, if you have a ball on a string and you are twirling it above your head, so it's in a horizontal plane, well, in that case, you've got gravity pulling it down, and in fact, a slight component of the tension would be holding it up, opposing gravity. But the main component of the tension would be pulling it in. Okay, tension doesn't push, it can only pull. So you get a force inward, once again. If this thing is going around in a circle, when it's over here, you'll also have an inward force. And we'll start to see the pattern, hopefully. That you always get a force pulling you inward for objects moving in circular motion. One more example, not to scale at all, but here is the sun, and here is the Earth. Granted, the orbit isn't perfectly circular, but it's pretty close. The only force acting between the Earth and the sun, or the only force acting on the Earth at all, is a gravitational force. That was a kind of a crooked arrow, but anyway. Pulling the Earth toward the sun. When the Earth is over here, gravity pulls it that way, and so forth. And it doesn't just act at these four places, all along its circular path. You get a gravitational force, and the gravitational force is constant, even though my arrows are not. So this leads to the idea of a central force, or what we call centripetal force. Not to be confused with centrifugal or centrifugal force. This means center seeking or toward the center, whereas centrifugal means away from the center. And that's a common misconception to think if things are going in a circle that they're being pulled to the outside of the circle. And a lot of that has to do with our common experience. If you are taking a turn to the left, you kind of feel like you fly to the outer edge of the car, to the right side of the car. There's no force throwing you that way. It's simply that you want to go in a straight line and the car is turning. So you fly to the right relative to the car, but what's really happening is the car is moving to the left and you are going straight. And then due to the friction on the seat, or if you smack against this wall, there will be a force pushing you toward the center, and so you will also go in a circle. If that weren't the case, you would just go in a straight line. If you were sitting on a frictionless seat and there were no door there, the car would turn and you would go straight. And that's what these tracks here are showing. For the car itself, it's friction between the tires and the road that pushes it toward the center. And if you're going too quickly, if there's not enough friction, you don't turn in a tight enough circle, and so you see these lines here. You'll go in a straighter trajectory than if you'd had enough frictional force pushing you toward the center to follow the curve of the road. A couple of other equations we're going to need for circular motion. We're going to have the frequency, which is the number of rotations around the circle per second. We also have the period, which is the time per rotation. I guess I should say rotations per time for frequency, but we tend to use seconds, and then we use units of hertz, where 1 hertz is 1 rotation per second. The period is the time per rotation, so as is pretty obvious, the frequency is the inverse of the period, so if you know one of those, you know the other. We can also talk about the speed going around the circle. Even though it's speed, we use v most of the time for velocity, even though it's the velocity is actually changing because your direction is changing. But anyway, if we think about speed as distance over time, if we're going in a circle, the distance around the circle is 2 pi r. And then the time to go around the circle once is a capital T here. So don't use lowercase t, please, because this corresponds to the time, a specific time to go around the circle once. So here are our different relations. Some of the problems will give you frequencies in revolutions per minute. This is common for like the engine speed of your car or a record player or something. If you have a record player that is 45 revolutions per minute, that's a frequency. Typically we want to convert that to hertz though, so all we have to do is divide that by 60 because we're essentially converting from revolutions per minute to revolutions, get rid of the per here, revolutions per second. Okay, so moving right along, that takes care of describing the motion a little bit, but I already mentioned that your velocity is not constant as you go around a circle. Your speed can be constant, and in fact we define uniform circular motion as that type of circular motion where you have a constant speed. But even if your speed is constant, your velocity is changing, and that's because velocity is speed and direction. So the length of this arrow here would be the same because that's the magnitude, that's the speed. But the direction of the arrow changes as you go around the circle. It is always tangent to the circle. So if I ever cut this string, then it will continue in the direction of its velocity, so the ball would fly out this way instantaneously. It wouldn't keep curving around for a little bit and then kind of dribble out of the circle or something. If you have that, back to that frisbee example, if you cut the frisbee in half, so you only have half a frisbee, and that ball rolls around here, as soon as it reaches the edge here, it will just go in a straight line. It will not curve around a little bit and then go in a straight line. That doesn't happen. Okay, so we have this velocity that is changing, and whenever we have a changing velocity, that is the definition of acceleration. Well, the rate of change of velocity is. So whenever you are undergoing circular motion, even if you have constant speed, you are accelerating. And the equation for acceleration we can derive from a bit of geometry. As we go around this circle and the direction of our velocity changes, if we imagine subtracting these two vectors, and if you remember, if you add vectors, you line up the tail with the tip. So there's different ways to subtract vectors. You can reverse the direction of them, or you can just line up the tails together, and then this vector here is what you get when you subtract the two vectors. So this is the delta v vector, and since acceleration is delta v over t, t is not a vector, so it's going to point in the direction of delta v. So for this case, the acceleration would point, I'm having my arrows bad tonight. Anyway, it will point in toward the center of the circle in the same direction as the force, which is what we would expect because of F equals ma. The force always points in the same direction as the acceleration. Now, to get an equation for acceleration, this type of acceleration, by the way, is called centripetal acceleration because it's toward the center, or your book sometimes calls it radial acceleration. So either way, centripetal, radial, those are radial, not radial. Those are synonymous, and we can derive a little expression for that. So if we think about this big triangle here made by the r's, the radii of our circle here, and this chord delta L, that delta theta is going to be the same as the delta theta here between our two velocity vectors. And so those are similar triangles. If we imagine that this delta L is close to it is an arc length, but if it's close to that chord length, then we can say that delta L is to R is approximately equal to delta V. Now these vectors have constant magnitude, so the magnitude of v1 equals the magnitude of v2, and I can just call that my constant speed. So it's approximately equal to that. And if we take the limit as delta t goes to 0, in that case, then delta theta goes to 0. I guess it's just an arrow, not a double arrow, but whatever. In that case, the chord will equal the arc length, and we can make this an equality symbol here. So, hooray for that. Alright, now if I think of my equation for acceleration in general, it's delta v over delta t. And if I solve this guy for delta v, I'm going to get delta v equals v delta L all over r. So I can plug that in here. I'm going to get v delta L over r, and then I've still got my delta t here. Well, delta L over delta t, that's a length over time, so that just gives me another velocity. This whole part here becomes another velocity. So I've got my two velocities, and I get velocity squared over the radius. So we call this the radius of curvature, and even if you're not going in a complete circle, if you're going in a segment of a circle, the physics doesn't know that you're going to stop going in a circle, so we still use that same r, which is the radius of a circle if you kept going into a complete circle. So centripetal acceleration is v squared all over r. You might not have any acceleration in the direction of the velocity because we said you have constant speed. Later on we'll look at when your speed changes, then you have an additional acceleration that we'll call the tangential acceleration. But for now we just have centripetal, sometimes also known as radial acceleration, given by this equation here. So as you go around the circle, that acceleration is always toward the middle, just like the force was always toward the middle. And that is why you go in a circle, because you're accelerating toward the center of the circle. Now, if we want to look at some examples, first we'll just look at some kind of qualitative examples of things going in circles. Let's take a Ferris wheel and some supports here for the Ferris wheel. As you go around this Ferris wheel, here's your little seat thing that you sit in. And we're going to look at these four locations and think about the forces that are acting on you. In those first examples I gave of the frisbee and the ball and the string and the earth going around the sun, there was only one force acting as the centripetal force, but that's not necessarily the case. You can have several forces acting as the centripetal force. You can have forces going in and some going out and canceling out. The centripetal force is always a net force, so it's the sum of the forces towards the center. Okay, and if the so it's equal, sum of the forces is always equal to ma, and if our acceleration is v squared over r, then this centripetal force or central force is going to be mv squared all over r. Okay, so pretty straightforward, just throw an m in there. So if we look at this, if I'm at the bottom, I've got a person sitting in here. I won't draw it because it'll be ugly. But I'm going in a circle. Let's say the Ferris wheel is going this way. It doesn't really matter. But I'm going to need a net force toward the center. And if I think about the forces acting on a person sitting there, well, you've got a gravitational force and you've got a normal force. And if I need a net force toward the center, that means that the normal force has got to be bigger than the gravitational force. And that is why if you're going around a ride like this, you actually feel a bit heavier. You might not feel it too much on a Ferris wheel, but you feel heavier when you're at the bottom because we don't perceive the gravitational force, we perceive the normal force. And the gravitational force isn't going to change, so the normal force can react to the dynamics of the system to grow or shrink. So when you're up here at the top, again, you've got gravity and normal force. Gravity is going to be constant. So in order to have a net force toward the center of the circle, again, your normal force needs to shrink. And that's why you kind of feel butterflies in your stomach. You feel like you're going to fly out of your seat. What's really happening is your seat is just not pushing as hard on you, and you perceive that as, feeling light, like you're going to fly. Now these ones on the sides here, in this case, you've got gravity and normal, and they're balanced because your acceleration is always towards the center. At this location, there's no vertical acceleration. So in that case, gravity and normal are the same over here. I still need a force pushing me toward the center of the circle. In this case, it would be a bit of friction, or if it's going fast enough, maybe like the safety bar. So there's going to be some other force here keeping you in. If there weren't, you would go in a straight line as the seat swooped back behind you. In this case, there might be some friction, or the back of the seat is pushing you toward the center. But in any case, you always have a net force toward the center. If we wanted to solve for some value, we could set up an equation here, say at the top here, just taking the larger force minus the smaller force, so we don't have to worry about negative signs. In that case, our net force would be gravity minus the normal force, and then we can set that equal to, when we're moving in a circle, the net force is equal to the centripetal force, so we can set that equal to mv squared over r. So that would be the equation that we could analyze depending on what information we're given when we're at the top. At the bottom, it's going to be pretty much the same thing, but now the normal force is bigger, so you would switch those around if you want to, again, avoid negative signs. Mv squared over r. Okay, not too bad. Now let's look at another example where we put some numbers on there. Let's say you have a car driving over a hill, something like this, and here is your beautiful automobile. And we'll go ahead and give some numbers now. Let's say the mass of your car is 500 kilograms. You are driving 20 meters per second over this hill, and the hill has a radius of curvature, even though it's not an entire circle. If it were an entire circle, we're going to say that the radius of curvature of this hill, what did I choose? 50 meters. That's not a 5. Try that again. 50 meters. And I want to know what the normal force is on the car at the top of the hill here. You could calculate it on the sides, but it would be more complicated. You would need to know angles and worry about all that stuff. So let's just do it at the very top of the hill there. So similar to the Ferris wheel case, when you are at the top, I need a downward force that is my net force. So that means gravity needs to be bigger than my normal force. Oops, sorry. So I still have some upward normal force, but it shrinks, makes you feel a little lighter as you go over that hill. And we can use that same equation that I had on the previous slide. So gravity minus the normal force is our centripetal force. So that's mv squared all over r. Gravity is going to be mg minus normal force. It's mv squared over r. Resist the temptation to cancel out the mass because you don't have a mass in the normal force term. And so you would be breaking algebra, and bad things happen when you do that. So rearranging things here, we get normal force equals mg minus mv squared over r. Plug in some numbers. We said the mass was 500. G is 9.8 minus a mass of 500. Our velocity was 20 meters per second squared, and the radius of curvature was 50. So that cancels out that becomes a 10. That's 400, so this term is 4,000. This is like half of 9.8, so it's 4,900. And subtract, and you get a normal force of 900 newtons, which is less than if you were on level ground. Then the normal force would be 4,900 newtons, so it's actually reduced significantly. Okay, so that's our first question. The next question we want to ask for this is, what is the maximum speed that we can drive over this hill without flying off the hill? And you'll see a number of questions like this. And in that case, as we go faster and faster over this hill, if you look at our equation for centripetal force, mv squared over r, as velocity increases, I need more centripetal force. Just like taking a turn faster, there's going to be more force required to make you turn at that faster speed. So gravity can't get any bigger, so as you go faster and faster, the normal force gets smaller and smaller. Well, you reach a point where the normal force goes to 0, and if you go faster than that, you don't have any additional downward net force to call upon. So in that case, you won't be able to stay on the hill. You will go in a larger circle. Since you made V bigger, physics dictates that R has to get bigger as well, so that you will go in a circle where the net force is just gravity, and it will be a larger circle. Well, if you don't go too fast, if you go to that point where the normal force just goes to 0, that is the maximum speed we can do before flying off the hill. So whenever you see a problem where it's asking maximum speed on a hill type of thing, in that case you want to set gravity equal to your centripetal force. We're just saying, we're using the same equation, but we're just saying normal force got small enough that it went away. So now we can say, not mv, sorry, mg equals mv squared over r. And mass cancels out, which is always fun. So that means the maximum speed doesn't depend on the weight of your car. It just depends on how fast you're going. Well, the maximum speed is how fast you're going, but it depends on the curvature of the road and on gravity. So if I want to solve for v, I'm going to get root g times r, square root of 9.8 times 50, and that works out to be 22.1 meters per second. So it turns out we were going pretty close to the maximum speed in the first example when we were going 20, but we could have gone a little faster and still not flown off the road. Alright, let's look now at something a bit more complex. Cars going around banked roads. If you have a flat road and you're taking a turn, then the normal force is balanced with gravity because you're not accelerating in the vertical direction. You just need a force pushing you toward the center of the circle, this guy here, and friction is what is going to supply that force. If you're on a perfectly slick sheet of ice, you will not be able to go in a circle. If it's perfectly flat, you will just go in a straight line. Okay, now things get more complicated if we are on a banked road like this. And if you're ever notice on like freeways and stuff, they actually bank them like this on purpose because it's harder to slide off the road this way. What happens here is, in addition to having some friction push you toward the center of the circle, since the normal force is now at an angle, a component of that pushes you toward the center. Another component still opposes gravity. So you can use the normal force to keep you going in a circle. That can become part of your centripetal acceleration or your centripetal force. This diagram here doesn't show friction, but you can have friction here as well. But it gets a little complicated because if you think about if this car were parked on a hill like this, well, gravity would want to pull it down the hill, right? So friction would be going this way to try to keep it from sliding down the hill. Now, a component of that friction is going to be canceling out. If you're stationary, this component of friction is going to balance with this component of the normal force. This component of the normal force plus that friction would balance with mg. But now as the car starts moving, you want a net force toward the center, just like you want an acceleration toward the center. So what's going to happen there, instead of having these guys balanced, friction is going to get smaller. So this component is smaller, so that leaves you, it doesn't completely cancel out this part of the normal force. And as you go faster, it will get smaller and smaller still, and you'll reach a certain location where there's no friction at all, and they call that the design speed of a road. The idea there is, even if you had your nice, smooth, frictionless piece of ice, you could still go around this road without flying off or sliding toward the middle if you were just going this perfect speed where the normal force provided the exact amount of centripetal force needed given the speed you're going and the curvature of the road. Okay, now if you go faster than that still, so we were going faster and faster and this was getting less until the friction went to 0. If we go faster where we need more force towards the center of the circle, more centripetal force than the normal force can supply, now friction will start pushing toward the middle of the circle. But it can't push straight that way. It can only push in the plane of the road. So friction then switches to pushing this direction. So no more friction there. If you're going faster than the design speed, friction will push here. So then a component of that pushes down, but a component of that goes toward the center of the circle. All right, now let's look at that design speed calculation. So going back to that perfect speed where you don't need friction to keep you from sliding towards the middle, or if you're going too fast, friction would keep you from sliding towards the edge. So if you're at that perfect speed where you need no friction at all, in that case, this component here, this x component of our normal force, is your centripetal force. Okay, so we can set that guy equal to mv squared over r. Now in that case, you don't have any vertical acceleration, so the vertical forces are balanced. There's no friction to worry about, so all you have is this up component of normal force with gravity. So you also have the equation Fn cos theta equals mg. Okay, so I can solve this guy for the normal force. So I get mg cos theta is my normal force, and then if I plug that back in up here, I'm going to come down here. So I've got mg cos theta for my normal force. Then I've got sine theta that comes along from here. And all of that equals mv squared over r. M's go away. Sine over cosine becomes tangent. So I've got g times tangent theta equals v squared all over r. And if I know a specific angle of my road, then I can solve for the velocity. But typically we know how fast we want the cars to be driving, and if I'm a civil engineer or something, I'm going to calculate the angle needed to have no friction needed at that speed and at the curvature of the road. So we're going to solve this guy for theta. So I get tangent theta equals v squared over gr, and then theta is just the arctangent of v squared over gr. So that is going to give me the proper angle given what's called the design speed of the road. Design speed. Alright, there you have it. Let's work through one of these examples. This is going to be a little bit long, so bear with me, but when you have to do a problem like this, you'll be happy that you've seen this before. So let's say that we've got an angle here of 10 degrees, and let's say that the radius of curvature of this road, from the bird's eye view, your radius of curvature here is, what did I say earlier, 200 meters. Okay. First of all, what is the design speed if that is the specs of our road? So in that case, we're going to rearrange that equation that I just solved for theta. I said theta was arctan of v squared over gr. Well, if I rearrange that sucker and solve for v, I get the square root of gr tangent theta. I'll assume you guys can do the algebra. Plug in 9.8 times the radius of curvature times tangent of 10 degrees, square root all of that, and you get 18.6 meters per second is the design speed of the road. Now what if I asked you what is the fastest you can go given a coefficient of friction of, what did I choose earlier, 0.2. 0.20 is our coefficient of friction. What is the maximum speed we can go on that road? Well, as I go fast, friction, as I mentioned earlier, is going to act in that direction to hold me on the road. So we're going to have to jump into this analysis here. If I think about, oh, by the way, when you're doing these banked road problems, this is one case where you have a ramp and you do not want to rotate your coordinate axis. The reason for that is your acceleration is in this direction, and if you rotate your axes, then you're going to have two different components of your acceleration, and life will not be good. Normally we had things sliding down a ramp where an acceleration was in the direction that friction is here, so that's why it was good to rotate it. In this case, please do not rotate your axes at all. So we can set up equations for the vertical and the horizontal forces and see if we can get something that will tell us about the velocity, the maximum velocity here. So horizontally, I've got this component of the normal force, so the x component of the normal force. I also have an x component of this friction force. None of gravity is horizontal from this perspective, and I need those things. They don't sum to 0. They are going to equal my centripetal force. So equals mv squared all over r. So there is v, and when I plug in an equation for my for friction, that's going to have the coefficient, that's going to correspond to the maximum amount of friction. So that's going to give us our maximum velocity. So essentially, if we can solve this equation for velocity, then we've got our answer. But we're not there yet. So the x component of the normal force is the normal force times cosine. No, we're used to using the cosine, but now we're dealing with that part there. So times sine of theta. X component of friction, in that case, here's theta. So I want the cosine for friction. So friction times cosine theta equals mv squared over r. And friction is mu times the normal force. So normal force sine theta plus mu times normal force cosine theta equals mv squared over r. In this case, we don't know the mass of the car. We don't know the normal force. We do know mu and we know theta and r, but we're not going to be able to get v just yet. I might as well factor out a normal force here. So one more step. Normal force is sine theta plus mu cosine theta equals mv squared over r. Now you might be tempted to say, oh, well, the vertical component of the normal force is balanced with gravity, like we saw when we were deriving the when we were looking at the design speed. Well, that's not actually true now, because we also have this vertical component of our friction that we have to deal with. The forces are still balanced vertically. There's no acceleration vertically. It's all horizontal. But now we've got the y component of our normal force equals the sum of gravity plus the y component of the friction force. Okay, so we've got these two equations here. Now, with a bit of algebra, we'll be able to solve this. So I'm going to solve this guy for the normal force, plug it back in there, and then we'll be in business. But it takes a bit of work. This friction here has got a normal force in it as well, right? So I've got Fn cos theta equals mg plus mu times the normal force sine theta. So if we do a bit of algebra, let's subtract this to the other side and factor out the normal force. So I've got normal force times cosine theta minus mu sine theta equals mg. And then if I divide that across, now I've got the normal force equals mg over cos theta minus mu sine theta. Okay, and now we're running out of room, but I'm going to try to squeeze this in. So if we bring this down here, I'm going to have that plugged in for my normal force. So mg, and then I still have this up top, sine theta plus mu cosine theta all over cosine theta plus mu sine theta. So close to canceling out, right? But unfortunately, they are not the same. Do not cancel them out. All right, so I was plugging that in there. All of that is still equal to mv squared over r. This, by the way, is decoration, as well as this line over here, so just ignore that. Masses cancel out, which was good because we weren't given the mass. We can multiply the r over here, take the square root of everything. That makes that go away. That's pretty ugly. We'll write it one more time. So v equals square root of rg sine theta plus mu cos theta divided by cos theta plus mu sine theta. And we can plug in our numbers, 9.8, 200, tens, 0.2. I won't write it again. and this works out to be 26.7 meters per second. So we can go faster than that design speed by quite a bit. If we go faster than this, there won't be enough friction and normal force, and we will start sliding up the road. We could also ask, what is the minimum speed? Well, there could be enough friction that you could be stopped, but other times you could have a minimum speed, if it's a steep angle, where if you're going too slow, you're not going to be able to go in that circle and you're going to start sliding towards the middle. If that's the case, to find that minimum speed, you're going to do an almost identical analysis, all of this wonderful algebra, but your friction, as I mentioned earlier, will be going in the other direction. So it's going to change the signs on your friction forces here. You're going to have negatives there, and so you'll end up with a number smaller than this for the minimum speed. All right, that was lots of fun. We'll see you next time.